So let's get started. Today we are doing Chapter 9 on virtual memory. And Chapter 9 is a continuation from Chapter 8 last week when we looked at main memory. So virtual memory, it's really not that much of a different concept except for some of the manipulation of the memory. So we'll take a look at the concept of it. I'll define virtual memory for you, the background information, look at demand paging. Look at CopyOnWrite, page replacement algorithms, and allocation of frames, along with the concept of thrashing memory mapped files, allocation of kernel memory, as well as some other considerations and some operating system examples. So the objective is to essentially define what this virtual memory environment is and explain the concept of demand paging. So last time we looked at, just refresh your memory, the concept of main memory. Main memory was the operating system's abstraction of your physical memory as it's translated into logical versus physical addressing. We looked at and defined the page table, and the page table was what was keeping track of the mapping itself from the physical to the logical. And in the page table we had things like dirty bits and clean, or actually just the dirty bit, whether it was set to on or off, meaning that the page was actually loaded versus not loading. We looked at the concept of the page fault, where the CPU goes over to the page table and finds out whether or not the page is actually loaded, and if it is, leave it alone and use it. If not, it triggers a page fault. Page fault is nothing more than a command that goes back and says to the kernel, try that again, because it's not loaded. So it goes back and it'll load the page that's missing. So what we're going to do is continue the concept, look at the page replacement aspect of it. How do we replace pages? Because eventually we're going to run out of room. Look at the concept of the page frame and the frames themselves, which we really haven't looked at yet, and then discuss the principles of the working set model in a little bit. I'm not going to elaborate too much on it, just give you an overview of it. So in terms of the background, virtual memory by definition is again the separation of the logical memory from the physical memory. When we talk about page replacement, we talk about managing the memory, we really refer to it as virtual. It could be called main memory, it could be called logical memory. There's different names for it. You never call it physical memory because it's not physical memory, it's a total operating system abstraction. But it's very commonly called virtual memory because modern day virtual memory managers are working with page replacement and they're working with terminology that would be appropriate for a main memory, virtual memory type of environment. So only part of the program needs to be in memory for execution. So going back to the beginning of what I was talking about in terms of memory, we have so much physical memory on the board, and then we take that physical memory and we map it into logical or virtual memory. It's still not going to be enough for everything that we have loaded, and it's not going to be enough to store 25, 30 copies of one program or something. Because if you think about multi-using environment, user double-clicks on something, it's going to load something in the memory. User double-clicks on something else again, it's also going to load it up into memory. All this stuff's not going to fit. So the concept of the virtual memory is basically a scheme for logically locating bits and pieces of the program that are needed when the program is running. And most virtual memory managers take a just-in-time sort of approach to it. Load it up into memory just when we need it. If we don't need it, don't load it up into memory. So the logical address space can therefore be much larger than the physical address space. And this allows address spaces to be shared by several different processes and allows more efficient process creation. So essentially what we're doing is loading stuff up into memory as minimal as possible so that we can preserve the resource and then allocate to as many processes as possible. So it does really facilitate, this virtual memory environment does really facilitate a nicely running system. Virtual memory can be implemented via demand paging or demand segmentation. I talked about paging last time. Paging is essentially the concept of taking a bunch of frames and allocating them to a page. And we have that page table that's keeping track of all of our pages that are associated with all of the frames. I'm not going to review all that stuff again. Go take a look at Lecture 8, last week's lecture, and you can get a good feel for what paging is about. Most of the virtual memory managers of today's operating systems are using a demand paging. And the demand paging basically says page it, but don't page it until it's needed. Wait, and then create the page, allocate the page. So it's going back to that just-in-time kind of characteristic. It's more effectively done when you load it in when it's needed. Because why load something if you don't need it? And then why unload something if you don't need it? So we delay the unloading until we need the space, and we delay the loading until we're actually going to use it. And then the segmentation is the programmer's or the user's perspective of the program instead of the memory perspective. So in terms of what demand segmentation is about, if we're using a segmentation approach, which we're using in some of these in most operating systems, we're using a combination of paging and segmentation. The demand segmentation is going to say, well, don't load it again, don't link the DLL or load the DLL or the shared object or whatever it is we happen to be looking at until it's needed. And a segmentation, going back to the concept, is nothing more than the abstraction of the program units. So it could be the modules, the classes, it could be libraries, it could be any kind of segment of the program that's loaded, that's used in terms of that abstraction. So here's our virtual memory that is larger than our physical memory, which is why well, I wouldn't say why, but it's one of the reasons why we're doing this. We only have so much physical memory. We can make it 10 times as big, 20 times as big if we want to, by just creating a virtual abstraction of it, which is what this slide is showing us. So this is the physical memory here, and the virtual memory is over here, and the memory mapping, and last time we looked at this we called this a page table, but it's really just a map. The map is going to take and map it to, this is the backing store over here on the side, or you could call it a swap drive. And it's going to take and map the physical locations to the virtual locations and give us that generic abstraction that comes out of it, because we don't want to look at physical addresses. Every physical address we see is going to be different, and it depends on the computer architecture. In fact, we don't even look at the physical memory, we look at the memory management unit. So if you wanted to, you could put like a little MMU right into between here, and the memory map would actually go to the MMU, which would be the physical memory. So, and then we're constantly swapping, and I talked about swapping, or the concept of swapping last time as well, when we need to swap something out, because this is going to fill up. The physical memory will fill up. And so if we have twice as much of it abstracted out over here, and we fill this up, and we want to add more to it, eventually we're going to have to unload something. In order to run that piece of memory, in order to actually execute the instruction, we need it loaded in the physical memory. So although this is, because another question that students usually come up with is, why do we need the physical memory then? Or what, is that? This is actually performing the memory functionality. It's mapped to many different virtual pages. And so we can selectively keep track of these virtual pages, load them and unload them when they're going to be run, when the process is actually getting CPU time. And they get loaded up in the physical memory. And then when we run out of physical memory, which is what we're going to do because we have twice as much paging going on, then take that, put it on the backing store. And then if it's on the backing store, this is a temporary memory layout that's formatted sort of like the physical memory. And so one piece will come out, one piece will come back in, and this is what is referred to as swapping. So this piece goes out, this piece comes back in, and then we can essentially create the abstraction so everything is loaded when it needs to be loaded. And that's where that valid or the dirty bit comes into. It's usually called a valid bit or a dirty bit. And it indicates if the page is over here and it's loaded and it's mapped, is it loaded right here? If it's not loaded right here, that's when that page fault occurs. And then the instruction has to go all the way back up to the start and say, okay, load it. It's not loaded, it's not valid. Because it could be here, but not here. And it's here. And if it's here and not here, it's an invalid page because the page that it's supposed to be mapped to out here is being used by somebody else. So this piece of physical memory belongs to somebody else. If we use it, we're going to get the wrong instruction, or we're going to get the wrong piece of data. So the whole key is in this mapping, and the memory map is where we're going to keep that valid or that invalid bit. The dirty bit is really referred to as, is it dirty? If we wrote it out once already, it's already on the backing store. If it hasn't changed, it hasn't gotten dirty. If it's changed, it's now a dirty piece of memory that needs to be cleaned up. So it needs to be written out again. Because the way this scheme works, we want to minimize the amount of swapping, minimize the amount of reading and writing, and have everything loaded just before it needs to be used. So if we do have to unload something to make room for something else, and the bit is dirty, we have to spend more time actually writing it to the backing store. If it's already in the backing store and it's been loaded, it needs to be unloaded, and it's clean, hasn't changed, well, why write it again? So you save yourself some extra time by not having to write it. And that's pretty much what we covered in the last lecture. So in this particular lecture, we're going to take the concept a little bit further and talk about what happens in terms of the page replacements, and in terms of the swapping, and in terms of how the system is actually working from an execution point of view. Here's the virtual memory space that is allocated to a process. And this is just memory from 0 to some maximum length. And in here we have the code. This is going to be the instructions. We have data that's allocated. And then we have the heap and the stack. I usually like to draw the stack down here and put the heap up here. But they're really just two growing together. The heap is empty memory that's left over, which is kind of like why I like to put it up here. But you figure, load everything up, and then you got some memory up here. And the memory up here is going to grow from this direction down this direction. In this particular case, because we switched it, we put it upside down. We got the heap, it's going to grow this way. The stack's going to grow this way. The stack is where all of our instructions are being placed for the CPU, for the CPU scheduler. So the data is going to be, we say integer I is equal to 1, integer b, integer h, create all these integers or floats or doubles and things, let's say, for creating a C program. And we have data bits, or data pieces. It'll be stored in this particular area along with other data pieces. When we have an instruction that says 1 plus 1 or I plus a is equal to something, assign it to something, those are instructions that are going to be loaded on a stack, and the data structure does work like a stack. You push on about 6 different instructions, or however big the stack is supposed to be. And then you pop off the instructions and they get executed, and then that's what the CPU is actually running. It's running those instructions, and the CPU scheduler is directing the traffic to whatever I/O or whatever resource those instructions happen to need, and then instruction will sit and get executed, hopefully. And then everything gets worked through the stack empties out. So the stack just naturally grows this way. When we dynamically allocate memory in a program, let's say we're back to C++ or C, and I talk about C or C++ in terms of this model because Java doesn't use this. Java runs in its own JVM, and the JVM organizes the process space. So Java is like an operating system on top of an operating system. And the concept is a little bit different because it's not allocated per process. The memory is actually configured slightly differently so that programs can actually share memory. This doesn't facilitate any memory sharing. In fact, this doesn't facilitate much except for a single process running on an island of its own. You can create another process inside of this, so we'd get a copy of it. But in terms of the way your modern day C++ program works in this runtime environment that's mimicked through this abstraction of this process that is nothing more than information loaded in memory, in terms of how that's running, each process is pretty much separated out abstraction-wise. And the hardest part in C++ programming and operating system manipulation is making the processes communicate in terms of inter-process communication, or leaving them alone and having them not write into each other's memory space. And in that particular case, everything works great until one process does something wrong and messes up another process. And then you get the blue screen of death and everything goes away and you reboot the computer, essentially. But going back to the heap concept, how does the heap fill up? Well, in a C++ program, when you say, give me a new object, give me a new integer, give me a new float, the new operator, which is creating dynamic memory, all the dynamic memory is loaded on the heap. So heap memory is going to be our dynamically allocated. If we're in a C, not a C++, would be the malloc, running a malloc, to allocate memory. And that grows up, the stack grows up. So one of two things is going to happen. We're going to get a stack overflow error. That would happen, let's say, if we had a program that had a recursive function call, and the recursive function call kept going over and over again but never stopped. That would fill up the stack and that would grow into the heap. Or in other cases, we would get out-of-memory error. And out-of-memory error would happen if we allocated dynamic memory with inside of the process, kept allocating and allocating and allocating, but never deallocated it. That would give us a memory overflow type of error message, which is really the only two things that really happen in this. I mean, either, or we have a bad instruction, we have bad code, or we have missing code, or the executable file has been hit by a virus and the code is in the wrong format now or something. But the data is handled by the stack instructions, so that doesn't usually go wrong either. So, in terms of shared libraries, and going back to the thing I said about Java, this is a Windows, pretty typical. And again, this is not exactly like the Windows runtime process, but it is close enough to be used as an example. And every textbook will use this particular representation to show you, if you could look at a process in memory, this is what it would look like. I've never actually seen a process in memory, personally, because it doesn't exist. It's an abstraction. But I think that was what it would look like. If we were looking more along the lines of a shared library, what we would have is the same components as we have before, and this is really two processes sharing the same piece of memory. This process over here has its own stack and heap and data and code. This one over here has its own set as well. And what we have in between is that shared memory, and the shared memory is going to go with the shared pages, and that's what they're going to have in common. So the allocation of this particular memory here is going to be at a different location. And if we use paging for this, we can actually facilitate inter-process communication, like what this slide is actually showing you, is inter-process communication. Because you have two processes that are sharing the same page in memory. If you do this, they can work on, a common task. They can share work. They can divide things out, and they can communicate with each other. So this model itself, this might actually be, let's say, for example, a dynamically linked library or a shared object. I'm sure everybody in here has heard of a DLL. In fact, you've really heard of one when you've seen the error messages come up on Windows systems, and you go, missing DLL. And you go, oh, what happened with that? Well, only on a Windows system do we have what a DLL stands for, Dynamically Linked Library. The DLL would be located in one of these shared spaces. And the DLL is nothing more than program source code similar to a driver that enables functionality. And the source code of the library, if you want to call it a library, maybe it would be a better way of describing it, might be used for, let's say, a printer or a fax machine, or some interface to some program that's running. Usually the DLL is associated with some resource that's on the computer somehow. And then the shared memory would make it so that one copy of that DLL could be used by every single process. And so in the Windows operating system, that's what we get, actually. You load up Windows, you reboot your computer. What you're getting is a bunch of DLLs. If you search, you probably have more DLLs than anything else on your computer. And those DLLs are loaded up into memory by the operating system at startup. And your programs are getting to them. So when you write Visual Studio, C++, or any Visual Basic, or any of the Visual ASPs, any of the Visual Studio packages, they're all using shared DLL libraries, and they're common Windows libraries for Windows MFC, the Microsoft Foundation classes, which gives you the window, gives you the controls. That's all native window, So you're not, or Windows, I should say. You're not reinventing the wheel. You're reusing, and you're reusing through DLLs, and the DLLs are linked, and how they're running is really efficient if you think about it. And I was kind of impressed when I first started reading about, this is back in the Windows 3.0 days. We didn't have as many, and then all of a sudden, past 3.0, like 95, but Windows 95-ish, all of a sudden this DLL came out like in widespread popularity. And then users can create their own DLLs as well. And it's efficient. And going back to what I said in the beginning of this lecture, we don't have enough memory to load everything that's humanly possible for every program. So if programs shared files and shared memory, we could load up certain dynamically linked libraries or shared objects. And the programs can call it and use it, similar to this slide here, access the shared library. And these are smaller, taking up less space. This is being shared. It's not being loaded and unloaded, loaded and unloaded. It just sits there. and it runs, and it provides services to all of the other processes, and it actually speeds up not only the memory usage, but it speeds up the operating system. And it makes it so that we can share things and we don't have to load our own copy. If we're loading our own copy and we had, let's say, functionality that was included in a DLL, we'd be doing this, and every single process would be loading it, would require more memory. So programs that use DLLs don't take up as much memory because they're all calling to the same program. But really, that wasn't even why it was invented either. The reason why it was invented is it kind of goes back to the Linux days. In Unix, they called them .SOs, or shared objects. And utilities like Perl and Python, and, well, I shouldn't say Python, Perl does it. We would have libraries or packages that are made by other people. And it was a way of compiling it, giving you a .so file, which was source code. I mean, excuse me, it was binary code. It wasn't source code that you could look and steal. And then you could create programs that ran on Perl, or you could create programs that ran, in fact, C and C++ run the same way. GNU-C runs the same way. In fact, they call them .o files, or object files. What we get is object code, and then the object code gets linked, and the link is basically happens at compile time for C or C++. Java implemented the same thing. So this is sort of like a Java environment as well, but instead of Java having DLL files or .o files, which are pretty much the same thing, or .so, so O would be object, SO would be shared object, DLL is dynamically linked library, all representing the same concept of taking binary code, sticking it out there, loading it up into memory, and having programs call it. So they don't have to make it themselves, they don't have to load it themselves, it's already loaded, and all the programs are using it. Well, Java did the same thing, except for all class files. So everything is a .class. They're all objects, because it's a true object-oriented environment. So every object that gets loaded is already loaded and is accessible by other objects. So you might think of this more along the lines of, instead of this runtime support, just look at all the shared memory, and instead of having each process being managed by each class, we have Java operating system support that goes out and manages all the memory and tells this class file where this class file is located. And we have resource managers essentially in Java that take the place of the CPU scheduler, take the place of the runtime environment, but do the same functionality. Orchestrate who's got what in memory, and if it's loaded, then use it essentially. So it's all dynamically linked, dynamically loaded. And one last thing to mention about, because you're getting a short lesson in runtime environment comparisons and contrasts as well in this, but it's really hard to talk about memory and virtual memory management without speaking of at least how the process abstraction is working in terms of the memory allocation. But taking this a little step further, the linking is one of the other components that's involved in this whole memory configuration. If we statically allocate everything, which means we create a .exe file or .com file, and we run it on the computer, everything is compiled. So it's not a hybrid, or it's not a script. It's a compiled kind of concept, and all of the objects are linked in together. So the object code is linked physically to the file. Switch that around. That's the C++ environment. So out here, our program that's running knows about the my printer or hp.dll file. It's going to load my HP printer or something. And it's already hard set in here where that's located. And it's already identified at a compile time. And they usually refer to that as statically linked libraries. So statically linked libraries happen at compile time. And the reason why we call those DLLs, because they are dynamically linked libraries, which means, better yet, don't statically link it, but put a stub in there, and the stub knows it needs a file, but the file can move. So as we're orchestrating this virtual memory, it doesn't matter where it is in memory, it doesn't matter as long as the name stays the same, the name of the file, and it gets loaded. If it's not loaded, it can load, and it can, at load time or at link time, link itself, establish the connection between it. And Java does that with everything. Microsoft Windows does it only with the DLLs. So the DLL is the dynamically linked portion, which means another vendor can make another DLL. You can download. In fact, what you're doing when you download updates is you're getting new DLL files most of the time. You can replace the DLL, unload the DLL, load the DLL again. It's a lot more flexible if you do it dynamically than it is to do it statically. And that's essentially what Java took advantage of in terms of creating its own. And a lot of people ask, well, why did Java have to create their own operating system for their own language? And it's because for this particular reason alone, the runtime environment is completely different. Everything's dynamic. There's nothing static anymore. And we have hybrid code. We get everything that's compiled but not linked. And it's compiled into an intermediate binary code, so it's not readable, although there's descramblers all over the place. But theoretically, it's made into runnable code that's in a binary format, machine kind of specific, but nothing's linked. So that's why when you compile Java files, you get, one program, you have 25 different class files out of that. And so how does that work? Well, you load it all in one directory, or you configure your Java environment to know where to look for the files. You load one file, and it will load the rest of the files for you automatically. It doesn't happen in Windows. It doesn't happen because Windows is using this kind of configuration. Java is using everything is this way. There's no separate process. It's just all the memory itself is being managed together. So anyway, that was a short lesson on the differences between the runtime environments between Java and Windows. But it comes in handy, especially to know what it is in terms of the background. Because when we start talking about swapping and demand paging, you're going to go, whoa, I don't understand what in the world you're talking about. Well, it gets down to the fact that you need a little background in how the processes are abstracted and how they're loaded in memory. So let's talk about demand paging. So maybe this will make more sense to you now. Demand paging occurs when you bring a page into memory only when it's needed. So I said about that just in time. So it takes up less I/O. In fact, it makes things load faster. Windows is what would be considered a demand paging environment, because what you're doing is loading up the operating system only when it's needed. Only the drivers that are being loaded are actually functioning. That's why people in the beginning used to go through and modify their registry, take out stuff they weren't using, because why load DLL files? And you can actually save yourself a little bit of memory. Now with Windows 7, it's a lot more optimized. In fact, I don't recommend changing or modifying that registry file, but if you think about the concept, if you go online and look at it and just Google registry cleanup or something, tons of third-party utilities out there to clean up the register, And the major focus on that was remove items that are needed. Interesting thing is the operating systems have changed. I mean, in the beginning that was the case, but with Windows 7 actually, and actually kind of started with XP. The later XP Service Pack 3, I believe, was implementing this. It didn't load everything that was in the registry. The registry can be as big as you want. It doesn't matter. Unless you're actually using the program, it's not going to get loaded. So, in fact, that's how Windows actually started loading up a little faster. Because why? If you're not going to use it, So now it loads up faster, but everything you run initially runs a little slower. Because it's got to load all the DLL support. It's got to load everything needed. But it's a lot more efficient, because you can have a smaller resource of memory, allocate a lot of stuff to it, and only use what you need to use. And it's kind of like planning ahead, thinking ahead. So less I/O is needed, less memory is needed, faster response time, and more users. More people can use the system simultaneously, more applications can run, it's more efficient. So paging is needed, or reference to it. Reference to pages, and this is where we're getting into that invalid reference. Is it in memory, not in memory? And I'll talk about a little bit about the concept in terms of if it's an invalid reference, it means we're going to have to abort and try it again, making sure we have a valid reference. And the reference itself is referring to, is it actually loaded? And is this frame, does it actually contain the information that's supposed to be in this page? And if not, then we have to fix it and make it contain what it needs to contain. And we have this thing called a lazy swapper. As I mentioned before, going back to this picture here, it said, showed us this. This is our swapping activity. So Our valid or invalid information is coming from if it's here and it's not here, it's invalid. It means we need to load it. If it's not here and it's over here, that's a swapping activity, with this being the backing store. The lazy swapper is going to leave it here. It's going to, unless we need the memory, why swap it? So lazy swapping waits till the last minute and says, you know, do we need to make room? If we don't need to make room, then don't do anything. So it never swaps a page into memory unless a page will be needed. Never pulls thing out unless it needs to be pulled out to make room. So it waits until the page is actually called, which means you load something up. You use it once, let's say, for example. You don't use it again. You may never, ever use it again. Maybe not for another week or so, but certainly not within the time that your computer is turned on in this particular session, as an example. Then you've saved yourself a lot of time because you didn't swap it in, you didn't swap it out, you just forgot about it. No problem. That was like one of the best things. The lazy swapping concept was actually pretty efficient in terms of when that was implemented. Swapping that deals with pages is going to be what's called a pager. So we have a pagers and we have swappers. Pagers are page replacement algorithms. And page replacement is what I'm going to get into next. That's where we have selections. That's where we can pick among different algorithms and work with the efficiency of the algorithm in terms of how we're going to facilitate our page replacement. So transfer of the page to memory to contiguous disk space. What we're looking at here, and going back to what we've looked at before in the beginning of last lecture on the main memory, talked about how inefficient contiguous allocation was. So we're not really allocating contiguously anymore. And contiguous, if you're not familiar with the word, just means we're sequentially locating the memory. So one piece, and the whole entire program is basically located together. If it is, you could pull the whole program out just really easily and then put the whole program back in if you wanted to. So here's program A. The entire program can be swapped out, and it could be loaded contiguously on the backing store. And then to swap it out, we would remove it, to swap it in, we take it from the backing store and we put it back in. Continuous memory is actually kind of interesting because not only is it fast and efficient and simple, it works, and primitive type of operating systems actually kind of use it. Only problem is it's not really good for multitasking, especially for most of our Windows systems, because we have hundreds of different programs out there. It's hard to allocate the spaces because of what I talked about last time. We have, like, for example, this is a hole right here. It's an empty space. Can't load a whole program in there. And I got 1, 2 holes up here, and I got 4 holes down here. It makes it hard to allocate a lot because it needs the whole line contiguous back to back in order to essentially use it. So in a perfect world, the swapping would be quite easy if we were using contiguous, and so would the memory management. However, we have to load a lot of stuff in there because users want to use a lot of programs. They're not going to use one program at a time. So when you don't use one program at a time, then you got to swap in and you got to swap out. And here's that valid invalid bit that I'm talking about. And the valid invalid bit gets set. Going back to this picture here. I should really put this slide in a little further back so I don't have to keep going back to it. And just to refresh your memory, because if you don't get the concept of the valid invalid bit, it doesn't make any sense. This is the last time I'll kind of go through it a little bit. We have a lot more virtual memory than we have physical memory. So these two never match. And when they don't match, we have an invalid bit. Because we're going to have something loaded here that's not loaded here. And if it's not loaded, it's invalid. Slight chance, however, if it's loaded here, it may be loaded here as well. If it is, it's valid. So what we want to do is minimize the number of invalid bits. Well, that's easier said than done. Because the higher the invalid number of bits, the slower the system runs, because it has to go back and load something. It's as if it was never loaded at all. So here's our page table from last time, and the page table, if you remember, had, well, the original format I gave you had 2 columns in it. One was the page and the offset. It was basically telling us where things were, from giving us the mapping from the logical to the physical. Now we can add a column, call it a valid and invalid bit. put it in here, put a V in here, it's probably going to be a 0 or a 1 to indicate you're never going to see a V or an I. In fact, this is an abstraction as well. It's going to be implemented probably in a hash table or something. And the V is going to say that it's valid or that it's in memory. And each page table entry is going to have one of these bits set. And they call it a bit because it's just an indicator. It's like a switch. So I says it's invalid or not in memory, V says it's valid. So a valid bit is one in which the page that you're looking at, and here we have actually referring to frames, the frames contain the pages, and the pages are valid for the running process that's trying to access it. If the pages don't belong to the process that's running that wants to use it, then it's invalid. And that means we have to basically have a page fault. Higher number of page faults, the more swapping. The swapping occurs when we have to pull it back out of the backing store and put it back into memory and get rid of what's in there because we have to fix the configuration. So those memory pages belong to that process. So the internal initial valid, the invalid bit is also set to I for all entries because it's going to be invalid initially. Nothing's loaded. Here's an example of a page table snapshot where we have the frame number and we have the valid and invalid bit on one side. So during the address translation, if the valid or invalid bit is in the page table entry, the I is basically giving us a page fault. So if it's invalid, we're getting a page fault. So here's the page table when some pages are not in main memory. So some of the pages aren't loaded. This is the logical memory, as I was talking about before, the physical memory. And this is kind of misleading because logical, this looks pretty big. The physical memory looks pretty big. This is really bigger in reality. This is, if I were to read, this actually comes out of the textbook. I didn't write the slide, but this I would probably make it like, twice as big as this, just to illustrate the point. Because people sometimes think that physical is bigger than logical. It's like, no. Physical costs money. Those are those boards you're sticking in the computer. You can have 8 to 10 gigs now, but you still had to pay at least $50, $100 now. Although memory is going down in price. And there was one time when it was expensive. This is always going to be smaller. This over here, the logical, is going to be huge. It's free. Yeah, it won't. It's the operating system. So the bigger the logical memory, however, there's a trade-off. The bigger the logical memory, the slower your operating system is going to run. If you go back to the concept of algorithms and efficiency, larger the search space, slower the efficiency. The more loops, the more work, the more complicated the algorithm is to go find it in memory. It's kind of like when you have this huge garage and it's hard to find anything in it when it's all filled up. But when it's empty, it's kind of easy to find stuff. But when it's all filled up, you have more stuff to go through. If you had an itsy-bitsy little garage and you were looking for something, you could probably go through the entire garage in an hour, maybe, or less, and find it easier. So, same concept with memory. There's a compromise. And I really couldn't even tell you, but it keeps getting bigger and bigger. Windows 7 has more memory, more logical memory allocated than previous versions do. But it got to a certain point, especially in the Vista days, where I don't think their problem with Vista was associated with memory, but you can get to a certain point where this is too big. It just takes too long. It makes the system run slower. And how much multiprocessing? Because this is the level of multiprocessing. And how much multiprocessing is the user really going to do? What are we going to run? An email program, a web browser, a Microsoft Word, a PowerPoint. And you can probably count up on your hands how many applications you're going to have running simultaneously. It's probably going to be less than 10, I would hope. If it is, and if Microsoft can predict that, and I'm sure they have some sort of a ratio that says, 8 programs. It might be interesting to figure out how many programs the average user does run simultaneously. That's how big you need to make the logical memory, enough to fit the average amount and then map it correctly. Here we have a page table that's mapping it, and in the page table we have an invalid bit because this one's valid. This one's got 4. 4 is loading A. So from the logical, A is right here, and C is number 2, and number 2 is mapped to number 6, and number 6 has C in it. So you can kind of see how the mapping is working. space 9 here. 9's got F in it. F is in 5 over here. This one's valid. These guys are invalid. And then if we were swapping it to the backing store, which is this guy over here, we would have this stuff loaded here as well. We may not necessarily have it loaded here. We're not going to load it here until this fills up. When this fills up, then we load to here, which is why you'll always see it in the diagrams with the backing store, sometimes also called the swap drive, located next to the physical memory, because that's where the physical memory is dumping out. It's like a temporary memory. This is formatted like this only because it has to dump back and forth. And that's the swapping in and out. And as I mentioned before, the swap drive concept is a Linux or Unix. I may not have mentioned it. It's a Linux or Unix abstraction. The Windows is a backing store abstraction. So it's just another word for a swap drive. In fact, even in current Windows builds, actually in current Windows builds as well, you can configure the swap drive. And the swap drive is kind of a tricky concept as well, going back to what I said about memory. If you can make unlimited resources, it's going to take longer to go through this. If this was like 1,000, I don't know, make it like 200 gigabytes of, memory. Your program, it'll probably take you 10 minutes for each program to load up or to start. Same thing happens here. If the backing store is too big, it takes too long to swap. And so it defeats that purpose too, makes it inefficient. So they always say to make the swap drive half the size of the memory. So if you have 2 gigs here, make this 1 gig or something. And there's a ratio where you can add to it, but you don't want to make it like as humanly big as possible, because in that particular case, everything's going to run slowly because the swap space is too big to search. So the page fault. You want to know what a page fault is, because this happens all the time. It's not an error. A lot of people, when they first hear the concept of the page fault, they go, "Oh, that's an error. It's a fault." Why they called it a fault, I don't know. But there's a reference to a page, and the first reference to that page will trap to the operating system. Trap is a software-generated interrupt. An interrupt normally comes from hardware, but this is a software-generated one because it's triggering a page fault because something's in memory is not in memory. It has nothing to do actually with the hardware. So if your CD-ROM, if the door breaks open on it, it won't shut properly because there's somebody put a coffee cup in the holder or something. Who knows what they do to the CD-ROM drives these days. Tray load breaks on it. It's going to send up an interrupt to the operating system. Interrupt handler is going to deal with it. Interrupt handler keeps track of all the activities that are going on, receives this information, puts it into a table, vector table, and kind of works with it, goes through and says each one of these has a code associated to it. So if it's the CD-ROM drive, then the code will be abort, or it will be disable the CD-ROM drive. This resource isn't going to work. When it catches a page fault as a trap that gets signaled, it goes into the same structure. Kernel looks at this and goes, "Oh, page fault. Oh, this means something's not loaded into memory," and then it deals with the page fault, which basically sends out another instruction that says, "Well, then load it into memory." So operating systems look at another table to decide if it's an invalid reference, if it is, abort. If not, if it's just not in memory at all, then load it in memory. So get the empty page, swap the page into the frame, reset the tables, and then reset the VIT to V to make sure we said, okay, now it's valid. Set it to V, and then run the instruction all over again. So restart the instruction that caused the page fault. So page faults make the operating system run slower. I'm going to make the operating system run slower because of all of these activities I just went through on the screen here, but it's going to essentially take CPU cycles to load something. It's more work, essentially. So to restart the instruction, we have what's called a block move. The block move goes from one memory location to another. It might be an auto increment, might be an auto decrement type of location. It's going to find the information that it needs to find from the backing store. If it doesn't find it from the backing store, it's going to load it from the main memory, from the secondary storage, wherever the code actually is located. Which actually kind of brings up another point that I should mention. I could probably mention it from this slide here too, because I like this slide a little bit better only because it shows you all the pieces put together. This backing store over here is your hard drive, believe it or not. It is a piece of your hard drive that's not allocated for you as secondary storage. It's allocated to the operating system for use as a backing store. So if you've ever wondered why, this is one of the reasons why, if you've ever wondered why your hard drive is always smaller, you don't get as much hard drive space as what the box told you. Like a 300 gig hard drive isn't going to give you 300 gigabytes of usable space, because some of it is going to be used for the backing store. If you install a swap drive, you set the Windows environment to use a swap, you're going to give even less hard drive space, because you'll have a backing store and a swap drive on there. But you know, hard drives are big these days. We're not really concerned about it. But if you've ever wondered why it never matches correctly, that's one of the reasons. And it's used for other things as well. Let's go through the process or the steps in handling a page fault. So here's the instruction over here that came out of the runtime environment. And following through with reference number 1, there's something that said load M. So they go, okay, wait, where's M? You know, so number 1 goes back to the page table. Everything originally just goes to the page table. And as I mentioned before, we can nest the page tables. We can have hierarchical page tables, or we can have one page table per process. This appears to be one page table per process, the way that this is designed. So when we come back here and we look for it in the page table, we have an I, and the I says it's invalid, which means it's not loaded. So M's not in memory. Because why load M if it's already in memory? So we're going to have to load it. So number 2 comes around and says, well, here's our trap. Send the page fault up. So the page fault goes to the operating system. You can call this the kernel if you want. And this is in the user mode, actually. So the page fault goes back down to the operating system from a kernel level. It says, hey, we have a page fault. And then following through step number 3, the page fault is going to be resolved. And it's going to be first resolved by looking at the backing store. So if this is huge, it's going to search all over in here and go, well, where is it? It's not here. Oh, then we got to load it from scratch. You know, that's a total waste of time. But luckily, it found it right here. So the backing store found it. The page is on the backing store. So it's going to come back out. And number 4 is going to bring the missing page and put it into the physical frame. It found a free frame from a free frame list, probably. Brought this page from the backing store, brought it in and loaded it into the frame. Now it's going to update the page table because we got to know that it's loaded. So then it resets the page table, comes back up here, resets it. This turns into a V, and then the instruction runs all over again. And then now it comes back and says, okay, now we're loaded. This is how our information is actually being loaded into memory. Every single time an instruction is run, page table is checked to see if it's valid or invalid, and then we have page faults. Imagine the concept of the page fault happening over and over and over again. Let's see what slide was that. Number 14. I like this one over here because it's actually this one will work. No, I like this other one because this one's bigger. Let's use this one because this I like this slide because this one in here is bigger. Virtual memory is bigger than the physical. Let's say we have a lot of stuff loaded right here. A lot of stuff. Like this is maybe 10 times as big as it looks like on the slide. And every single hit is a page fault. Everything's invalid because this can only get 1, 2, 3. We get maybe less than half of what we have over here. Every single instruction that we're running is causing a page fault, and we're swapping out, swapping in, swapping out, swapping in constantly. This is what's called thrashing. A lot of work's getting done. The CPU is really busy at this point. It's taking and accessing all these page faults and working with it and loading every stuff in. But at any one moment in time, there's not enough room here to fit everything here. The process is too big. Let's say we have 2 huge processes running that are both running simultaneously that we're trying to use. Everything is going to slow down to not a complete stop, but it's going to look like it because the CPU is going to be busy swapping in, swapping out, swapping in, swapping out, trying to make this whole and complete, but it never gets to that point. So thrashing is when the computer is busy doing absolutely nothing but swapping, and none of your programs, nothing is working. That's when you usually get the blue screen of death. But you don't get it anymore. Now it's a black screen. But you don't even get that anymore. Instead you get memory fault error, or you get oh, there's a classic message that comes up that says, system is low on memory. If your system says it's low on memory, it's because your virtual memory manager is thrashing. It's thrashing too much. And when it says that, it wants you to shut the computer off and turn it back on. Because there's stuff loaded on the backing store, there's stuff loaded in memory that is still there, but you may or may not necessarily be using it because there was a mistake or something happened in the algorithm. And the computer is thrashing too much. The operating system mechanism is loading, unloading, loading, unloading. Swapping is way too high as a percentage. And how do we know the percentage? Let's go into the performance for a few minutes. So the operating system itself can keep its own statistics. It knows when it's thrashing. It knows when to send up the blue screen of death. It knows when to put the low on memory, out of memory. And when how can I be out of memory? I got 10 gigs of RAM on this thing. It's possible if the algorithm is messed up or something happened. But let's take a look at performance of demand paging for a second. If the page fault rate can be measured, and the page fault rate is going to tell us how efficient and how fast the system is running. The higher the page fault rate, the slower the system. We get it to a certain point, we end up in the thrashing category, and at that particular point, just turn the thing off and turn it back on. Here we have 0 is less than or equal to P, which is going to be less than or equal to 1.0. So if P is equal to 0, there's no page faults. So if P is equal to 1, every reference is a page fault. So it's going to range from 0 to 1, and we want it to be 0. We want it to be empty. Because we have what's called the efficient access time, or the EAT, which is equal to 1 minus P, where we have X is the memory access plus the page fault overhead. Page fault overhead is the swapping, plus the swap out, plus the swap in, plus the restart of the overhead. And then we can kind of figure out, and our operating system is going to be doing this because it's trying to keep track of, do you have the memory management correct? If you've ever gone into the Windows control panel, into system, and into environment, or into and looked at some of the settings, let Windows adjust it. A lot of people try to put their own numbers in there, and make it 1024, and make it this and make it that, and they try to configure it. The thing is, the Windows operating system the kernel is calculating all this information, and it can adjust itself. It can make the backing store bigger, make the virtual memory smaller, can reconfigure itself to get an acceptable EAT, or an acceptable speed. Where the user, you're not knowing exactly what's going on. That's why I was wondering, why do people set that themselves? When, just let the operating system do it automatically. So here's a demand paging example, where we have the memory access time is equal to 200 nanoseconds. The average page fault service time is, let's say, equal to 8 milliseconds. Because each one of those page faults that occurs has what's called a service time associated with it. And the service time is how long does it take to fix the page fault? Put the piece of memory from the backing store back into the memory so we can use it. So the EAT is going to be equal to 1 minus P times 200 times P. Well, anyway, I'm not going to go through the entire calculation. You can go through it on your own. But we can add the same formula for the EAT that we've seen on the previous slide, plug the numbers in, and you can kind of figure out that how, as a particular example, how effective is it going to be. So if one access out of 1,000 causes a page fault, in this particular example, then the EAT is 8.2 microseconds. This is a slowdown by a factor of 40. So we can kind of tell, given the page fault service time, given the memory access time, and given the page fault rate, how many page faults we have, we're going to say how much is this demand paging, how much of it is slowing down our system, how is it making it inefficient, essentially. But this inefficiency is due to our multitasking, our non-contiguous memory allocation. If we go back to a contiguous memory allocation, we have a better world, but we can't multitask. We can't load everything up. It doesn't work that way. So we have some issues in terms of process creation. So we have virtual memory that allows other benefits during the process creation. We can do what's called a CopyOnWrite, or we could do memory mapped files, and we'll talk about later. CopyOnWrite is kind of an interesting concept, and this is when we're creating these processes. Well, going back, I'm not going to go back to that slide in the beginning, but We looked at the process space and we were allocating that. Our CopyOnWrite allows both parent and child processes to identically share the same process memory. So it's the same pages in memory. This can make the system a lot more efficient. So, if we go back to chapter 3 and we talk about process creation, when we create a process, it's allocating that memory, which is why I kind of wanted to talk about that process space in the beginning here. And it's got its own layout, and it's already configured. The more processes that one process creates, or the more processes in general that we create, the more memory that's going to be allocated. So one of the ways that you can make the system more efficient is to make child processes share the parent process memory space, because not both of them are going to be running at the same time. One process that forks another process, is referred to as the child process. The child process is going to run while the parent waits for the child. Why can't they share the same memory space? Why do we have to burden the system by creating another process out of that? So that makes the CopyOnWrite makes the process creation run faster, because we're not trying to go allocate, swap stuff out, swap stuff in, and create a new process and go through the same identical work that it takes to create the original process. So it's a lot easier. If either process modifies a shared space, modifies a share only then is that page copied as well. So if the child gets a copy of the parent when it is created, then we don't have to worry about it until a change happens. So if a change happens, only when the change is happening do we worry about it, do we copy it. Otherwise we just leave it alone, and the process essentially doesn't need to do anything. The CopyOnWrite allows more efficient process creation, as only modified pages are also copied. Which is kind of interesting, because if we've got to write something out, why waste, going back to what I said about before on the backing stone and stuff like that, why waste writing something if it hasn't been changed? So we copy the information over when it's been changed, and so which is where this CopyOnWrite is coming from. If there's been a write, then update it. If not, no writes, just reads to the memory, leave it alone. We don't have to worry about it. So that CopyOnWrite as a concept can actually save processing time. Free pages are allocated from a pool of zeroed out pages that are emptied, essentially. Here's a before process 1 modifies page C. We've got process 1 over here, process 2 over here. We have two processes sharing. Unless something is written, we don't have to worry about writing it. So we have we have page A, B, and C, and that both in physical memory, they're both process 1 and process 2. This is, let's say process 2 is a child of process 1. And after the process 1 modifies page C, we don't actually have to do anything. Or no, actually after it modifies page C, it should be writing page C. This slide, I keep forgetting to edit this PowerPoint presentation, but this slide is wrong because these two should be going away, and the C is the only one that really needs to be modified. So after process 1 modifies page C, C would be updated. And but this slide here and this slide here are identical, which is kind of pointless in terms of what's going on. So this is the before, this is the after. But page C would be updated. So I have to edit this slide set next time I do this. So what happens if there's no free frame? We have page replacement. So as I mentioned before, pages have frames. Frames get loaded up into the page table, and they get allocated toward the virtual memory. So page replacement finds some page in memory, but not really in use, and swaps it out. That would be the perfect case scenario. If there's a if there's a page in memory and it's not being used, not always the case. So you have to think about, well, what about the least recently used, or what about the last, maybe use a time on it. Which one hasn't been used in a long time? Or which page is used a lot? Don't swap that one out. So we have selections, and the whole theory of the page replacement algorithm is to find the best routine that's going to do the lowest number of swapping for us. So we have an algorithm, and we have, this is kind of deceiving. I should put an S on the end of this when I modify algorithms to do page replacement. And we have performance to consider. We want an algorithm which will result in a minimum number of page faults, because we don't like page faults. And the same page may be brought into memory several different times. So we want to minimize how many times we're bringing it into memory as well. So page replacement prevents overallocation of memory by modifying page fault service routines to include page replacement. So the service routine of the page fault, when the page fault occurs, is going to perform the page replacement. So it's not going to randomly just do something. It's going to actually follow this algorithm technique. So here's where that dirty bit comes into. So dirty is modified. So use a modified bit or a dirty bit. The old word used to be dirty, and because then people say, well, wait a minute, it's not really dirty. It's just modified. Dirty gives that connotation of not being clean. Like it's dirty, it's messed up, it's garbage. When it really isn't garbage. It's not really dirty. It's just modified. So newer textbooks, this was like till about maybe the late 80s, and all of a sudden we started modified bit. But people I like dirty bit actually. So it sounds better. It sounds more scientific, the dirty bit. I don't know. But, so it's interesting that young kids' bachelor's degree programs, they have the modified bit. They don't use the word dirty anymore. So it's like the modified bit. Oh, you mean dirty bit? Yes. That's what I'm talking about. It's the page that changed. It got modified. So to reduce the overhead of the page transfers, you only modify pages that are written to the disk. If the page, only write modified pages are written to the disk, you only write the page if it has changed. If it has not changed, it's not dirty. No dirty bit set, and the dirty bit's either going to be set or not set. Then don't write it, because writing is going to be expensive time-wise. So page replacement completes separation between the logical memory and the physical memory. Large virtual memory can be provided on a smaller physical memory scale. So when we introduce page replacement to the concept, we don't even need as much physical memory anymore. So we can get systems that have a very small physical memory, for which we're using page replacement algorithms that are very fast. And then all of a sudden, we can essentially have a system that runs a lot quicker than given a lot more memory. So your choices are load up a lot of memory, have a very lousy page replacement, and hope it never works. Or hopefully you will never have to use the page replacement, because the more memory, physical memory you have, the less page replacement you're going to need. Or make this small and have a really good page replacement algorithm, which is trade-offs, and this is expensive. So if you're building an operating system, it's kind of like one of the decisions you have to make. It's like, and every operating system is going to have specs on the box. In fact, I think Windows 7, I can't remember what it says. I think it's 4 gigs now. I think the original version. Does anyone know how much memory does Windows 7 require? I think it's like 4 gigs, isn't it? RAM. It used to be. Remember when Windows XP came out? It was 1 gig. And you had to. No, actually, it was 512. You could load it with 512. But everybody upgraded it to 1 gig, and then everyone went 2 gig standard. 2 gig is pretty good on a Windows XP system. And then I believe 7 doubled it or something. I could be wrong completely. So it might be an interesting experiment. Go online and find what's the minimum memory requirement. Here's the interesting thing. The minimum memory requirement is for the operating system. So, I know the 512 was, I'm pretty sure, I'm 99.9% positive the minimum requirement was 512 on an XP. So let me use that number as an example. The operating system will run just fine. And if anyone ever had an XP system that had 512 on it, probably noticed it kind of runs a little slow otherwise. Because it's not using, it's not optimizing this memory management scheme. When you make it 1 gig, let's say for example, you add in more on there, less page replacement going on. So more memory, bigger space. So there's a trade-off between what happens when the page replacement doesn't have to occur. Then we get to a certain point, and each operating system has a maximum. And it will only work, it will only use a certain amount of added on RAM. And at that point, you could put on all the RAM you want, and it's not going to do it. It's not going to improve your page replacement because your operating system isn't going to use it, and it's not going to provide you any speed. It's like you have a car as an example. Let's say you add something to the engine but you don't hook it up. You put on a accelerated something or other, but it's not connected to anything. Well, that's what happens. You can't do it because most manufacturers will tell you, it only goes to a certain point. It goes from 2 to 8 gigs or something. And then after that point, the algorithm, which is already preset to work with a pre-configured environment, isn't even going to notice it. So we had that actually with NT systems. We took I believe there's no more of a requirement because the hardware itself is setting the requirement. Like your board will only take 4 gigs of RAM or 2 gigs of RAM. And it's only expandable to a certain point. And that limit is always lower than what the operating system can take. So we didn't really have a problem. But in the beginning, we did sort of have a problem. And I think it was with the NT system that people were loading on, because NT as an operating system was being installed on some more sophisticated, higher-end hardware because it was meant to be servers. So people really invested a lot of money into the hardware. You put 2 gigs on it, it doesn't read it. It only uses 1 gig. It's kind of a waste, actually. But NT's not even on the market anymore, and we've kind of worked past that concept. But the need for the page replacement algorithm is demonstrated in the slide you've been staring at. And this is sort of like that flow chart I went through with the page fault, where we have a PC actually stands for program counter. And so in the runtime environment, the program counter keeps track of the instruction. The instruction comes in and says, okay, load M. And this is the logical memory for user number 1. This is the logical memory for user number 2, and etc., which is basically how the system is separated out, usually by user, or by login, I should say. And then we have page table for number 1, we have page table for number 2 in this particular configuration. And this is arbitrary. It doesn't necessarily have to be done this way. We get 1 page table for both users if we wanted to. On the right-hand column, we have our valid or invalid, and we have the page here. And this one's empty. We have 1 invalid, and these are all loaded. And out here, going back there, we can map it through to the physical, and then we have some stuff out here. And eventually, we're going to have to replace because we're going to run out. This is going to fill up. So page replacement algorithms replace the items in the pages that are mapped to the physical memory, that are mapped to the logical memory from the particular user. So you could say that this is the logical, this is the virtual, this is the physical. And the virtual really does work with page replacement in terms of what's going on. And the page replacement is nothing more than going to do the swap for us, load it into memory. Because eventually these guys are going to fill up this, and we have no other choice. Basic page replacement. So what I'm going to kind of go through is about 3 or 4 different, and I'll go through them quickly, just 3 or 4 different examples about how page replacement is done. And these are sort of the beginning page replacement algorithms. There's a lot more sophisticated algorithms on the market. But essentially, looking at this as our starting point, this is what we are juggling around. We find a location on the desired page on the disk. Okay, we find a free frame. If there's a free frame, we use it. If not, we have to create one. And that's where we get victims. So if there's no free frame, we use a page replacement algorithm to select a victim. And the victim might be out here if we're keeping track. And we're adding more overhead now to the system. If we want to keep track and say, well, we have it, user number 1 is using a lot, user number 2's got a lot of stuff loaded already, So they all have a lot of stuff loaded, which means we got to take if user number 1 wants to do something, we might have to remove something from user number 2. Or maybe we're going to keep track of it per user. We have to find a victim. The victim is going to be someone who might actually be valid, well, it is valid for somebody else. Something that might actually be in use, but we can't. We have to it's a sacrifice. We have to pull it out. So we bring the desired page into memory, into the newly free frame that is created. And then we update the page and the frame tables to indicate that this is now valid, and then we restart the process. So the basic page replacement is doing nothing more than picking the victim and using, okay, now you're going away, now we're going to load some stuff into you, and now you're now going to represent the page. And here's our victim out here. We swap out the victim page, because we're going to keep it, and then we swap back in the page that we actually needed to be loaded. And then we update the page table. And we update the page table with, now we have this free frame that was valid, or F got loaded in here where the victim frame was. So we changed to invalid from the first step when we swapped it out, and then we swapped it back in and we reset the page table for the new page. So it's nothing more, the page replacement by concept is nothing more than taking something that's in memory, unloading it, taking something that's been unloaded, putting it back into memory and putting it back into the same spot, into that victim location where we pulled something out of. So, I don't know why students have a hard time understanding this. You guys seem to, no questions or anything, so you guys seem to be getting it, but yeah. It's funny, I won't know until the final exam when I ask you a question about page replacement, and then people will answer in such a funny, different way. It's like, what is swapping? It's swapping, and it's like, and then you answer, you pick the item on the multiple choice that has nothing to do with memory, and then I go, oh, wow, that's an interesting way of thinking about swapping. I never thought of it that way before. Page replacement algorithms. You want the lowest number of page faults. That's something actually, I know I'm going to ask you questions about page faults, and I'm going to ask you questions about page replacement algorithms and stuff like that. That's fun. And CPU scheduling, that stuff's fun too. So you evaluate the algorithm by running on a particular string of memory references. You have a reference string, let's say for example, and then you compute the number of page faults on that string. So what we're going to do is run through an example with this particular example string here, and we're going to compare the number of page faults. The one with the lowest number of page faults is going to give us the best, most efficient runtime. So here's our reference string, and it's just a bunch of references, sort of like in this particular example here when using all of these, ones and D's and E's and F's and whatever. We're just going to take this reference string and compare it. So here's a graph of page faults versus number of frames. So the number of frames that are available versus the number of page faults. When the frames are small, we have one page as an example. We have really small, less than 512. Number of frames is very, very small. We have a lot of page faults. More frames, fewer page faults, lower number, so which is why the kind of curve goes down this way. About 5 frames, it looks like in our particular example, it's kind of leveling off. So even if we had 10 frames, it's probably going to still generate four page faults or something. So it's kind of an interesting shaped curve that's predictable in terms of most of our algorithms, and this is kind of the efficiency, the graph that we're going to kind of compare things to. The basic first in, first out algorithm. So here's our reference stream from the previous slide, and we're going to start comparing these algorithms. We have 3 frames, let's say, so our search space is 3, so 3 pages can be in memory at a time per process. Now imagine up here, the 3 is right here, which, we're going to come out with an average number of page faults. It looks like about 6, maybe 5, 5.5. So we have 9 pages or 10 pages that we're going to load in, but we only have 3 frames. So we have, in terms of our 3-frame example with 1, 2, 3, we have these particular items that are going to be loaded into it. On 4 frames, we could come out with, let's say, a 10-page fault versus a 9-page fault. We added another page. So Bradley's anomaly, the more frames, the more number of page faults, which is kind of interesting. So the more frames we have, the higher the page fault rate could possibly come in. And this is using a first in, first out, because we have more swap. Well, we're going to have more swapping that's going on in terms of this configuration. So in terms of our reference string, using a first in, first out, and the first in, first out is going to say we started with 1, 2, 1, 2, 3, and then we have 4, 1, 4, 1, 2, and then we have here 5. Did I get numbers wrong here? Oh, I had to swap out. We had some page faults going on here. And we eventually had the 5, the 3, and the 4 loaded in. We started out okay. The first in is the first out, because we're going to fill it up in order of how big things are from our first in. And then the later ones that come in are going to have a problem because of the way this configuration, the way these frames are organized. So this is another representation of the same example in terms of the page frames. and how the page frames are loaded in. So this is just showing you the sequence. So number 1 was the 7, and then we had the 7 and the 0, the 7 and 0 and the 1. I'm not going to go through it, but this is essentially the logic of what's going on here. 0 is nothing. So, or no, 0, actually 0 got loaded in here somewhere. He's down here. 2, 0, 3, 2, 0, well, that got swapped out, 3. But we're loading up those pages with the reference string. And then here's our number of frames. As our number of frames goes higher, or excuse me, goes bigger, our number of page faults go down. So we have that. We have the sort of average kind of curve that happens. And what we're going to have is essentially the same type of graph for each one of these algorithms. Optimal algorithm. So replace the pages that will not be used for the longest number of time, longest period of time. And something to note here, this first and first, this is an algorithm for page faults, excuse me, for page replacement. And it follows through the basic anomaly with saying, you know, the more frames, the more number of page faults. There's gets to a certain point where it, you know, the number of frames balances. And we're filling it up and we're unloading it in a first in, first out. If we take and use an optimal algorithm approach to this, in our case here we might have 4 frames in this example, 1, 2, 3, 4, and we have 6 page faults because we're going to use it 1, 2, 3, 4, 4. We're going to have a page fault. We're going to be loading stuff in. How do we know this? Well, it's used for measuring how well our algorithm is going to actually be performed. So we have to have some sort of criteria for measuring, and what we generally come up with is how many page faults are going to occur, given how many frame size. And then we can configure, given the amount of memory that we want in our virtual memory, how big to make that to match the physical to reduce the number of page faults. It will get to a certain point where the number of page faults will increase versus decreasing. So in terms of our optimal page replacement, this is just yet another example of loading the string in terms of how we're going to load it. And the optimal one is only going to replace it. It's not used for the replace pages that will not be used for the longest period of time in terms of the strategy, because you know, replace the ones that aren't going to be accessed over and over again. So we'll minimize the amount of swapping that we have to do. Or the least recently used algorithm, which is a little bit more promising, actually. In terms of our reference string, using the same one, loading that up into the sequential, you know, one right after the other. We could implement it, and here's the interesting thing. So the first in, first out algorithm here takes absolutely no overhead in terms of the algorithm outside of the configuration of how you're going to load the reference string and how you're going to allocate it. And then you can figure out, well, with 3 I got 9, with 4 I got 10, so I got, wow, you know, my page faults are going up. So at a certain point, page faults aren't going to go up anymore. And that's pretty much the calculation that we have to work with that. On the optimal algorithm, we sort of have to figure out which victim we're going to pick. And the victim that we pick is going to be on the theory of the longest, you know, the page that will not be used for the longest period of time. So we're not going to unload operating system stuff. We're going to be biased, essentially. And we're going to predetermine what we're going to unload as a victim. In terms of our least recently used algorithm, we actually have to keep track. And this is where counting or indexes come into place. So in terms of a counter implementation, we can keep track and count which page has been the least recently used. And then we take that one, we swap it out, on a goal of basically creating less swapping, fewer number of page faults. So every page entry has a counter. Well, there's extra overwork. There's, going back to what I said about the algorithms and the efficiency, well, it's the search space, but it's also number of loops, complexity in terms of what's going on with that algorithm. This is going to add to the this is going to decrease from the efficiency of the algorithm because you're adding more complexity to it. You're going to put in a counter for each one of the pieces. Every time a page is referenced through the entry, there's going to be a copy of the clock into the counter. You're going to update the counter. So when a page needs to be changed, you look at the counters to determine which ones you're going to change, which one you're going to take out, the least recently used, hopefully. And so the way this works, where we're at with our reference string here, we're loading it in, and this kind of mimics, you know, if you were going to take the least recently used page, you know, I'm not going to show you the counter, but this is essentially the execution that would happen in a sequential kind of way. We can implement it in a stack, which would eliminate the counter. So keep a stack of page numbers in a double linked form. So we have a page reference, and then we move it up to the top. Stack implementation for least recently used is very promising because it doesn't add to the algorithm complexity. It's using a data structure to organize the strings, so it requires 6 pointers to be changed. You have to constantly update the pointers. However, there's no search for a replacement. There's no thinking. So there's no search. Faster. You're not going to be slowed down by the search. So if you use a stack to record the most recently paged reference, you just pop it off the stack. So now we have it like 2 would be replaced, 1, 7 here, 7, 2. Excuse me, after I pulled off 2 and 1, or 0, I would have 7, put 7 back on, the stack after B. Here's B, 7's coming back on. And so we would pop one off, push one back on, pop one off, push one back on, and use the data structure instead of having to use a counter or another algorithm to mimic that. So we have least recently used approximation algorithms. So we could keep a reference bit so that each page associates a bit, and here we go again with more bits that we're adding to the configuration. So when the page is referenced, we set the bit to 1, and we replace the 1 with a 0 if 1 exists. We don't know the order. We don't really care about the order. Instead, we're sort of keeping an approximation by setting an on or an off, essentially. And then we have a second chance. The second chance would need a reference bit and a clock replacement. And so if the page is replaced in the clock order, has a reference bit of equal to 1 is equal to 1. If that's the case, we set the reference bit to 0, we leave the page in memory, and we replace the next page. So we can approximate with a little bit more efficiency than running a true algorithm, either using a stack or a counter implementation. And it shows promising. With our second chance clock and our page replacement algorithm here, we can say that this is going to be the next victim, and then that's going to be the next victim. So we can run a circular queue of pages and essentially go through with an approximation, also with a stack, but we're not keeping very much information. So the lowest amount of information that you can keep in terms of the algorithm, the more simple you can make the algorithm, and if you could use approximations for it, then your algorithm is going to run efficient, or a lot faster than it would otherwise, either by keeping a reference bit or a second chance kind of opportunity. Counting algorithms. So keep a counter of the number of references that have been made to each page. Could you imagine the amount of overhead associated with that? Every time you accessed something in memory, a counter was increased. So these recently, you can come out with the most frequently used or the least frequently used algorithm. If you're keeping a counter, the least frequently used is going to replace the smallest count. The most frequently used is based on the algorithm of the page with the smallest count that is probably just brought in and has yet to be used. So we can kind of keep, in fact, there's another philosophy to this as well that wasn't mentioned. Least recently used is kind of giving you the impression that something is loaded in and maybe it's not being used anymore. Like the user has moved on, they're doing more work. And you have to imagine it's kind of like the psychology of the user that the operating system designer is using with that. And then, the concept of, well, something is used a lot, and then it was just brought into memory, which means, the user could have brought it up, and then now is going to go on to something else. And if you just brought it up into memory, are you still using it? So it's kind of like operating system psychology of the user as to which victim was actually more appropriate. In terms of the allocation of the frames, and it depends on whatever configuration you're going to make it, and whatever configuration for the allocation of the frames is going to essentially be associated with the type of algorithm that you're going to use to allocate the frames. Each process needs a minimum number of frames that's going to be associated with it, and it's preset. You could, if you wanted to, you could not make each process have an equal amount of memory. And when I talked about, I believe it was chapter 3 a couple weeks back, we talked about processes and allocation of processes and the amount of memory that's allocated. Most systems are going to use a fair set amount. Every process is going to get the same amount of memory. But we could have different priorities of processes, add them, allocate them more memory. And if that's the case, then they're going to occupy a higher percentage of the memory that's available. So your replacement algorithm might be adjusted to not touch higher percentage frames versus lower percentage ones, depending upon the nature of the system. Now going back into what's the user doing, well, we can also consider the kernel as a separate psychology of the kernel. Like what's the kernel going to be doing with that memory? Which is kind of like the scheme of why most kernel processes are always, in every operating system, they're always loaded at the lower level because they're accessed more often. So you want the access to the memory to be optimal, and that would be like the seek time, to be very optimal for the operating system, for the kernel, because those are the most important processes. They're going to be used constantly. So the least recently used stuff that the user's loading, we'll put it on top, put it far away, so that it's not going to be found as quickly, but it's more swappable, essentially. And then you could segment out the memory if you wanted to, and don't swap out anything kernel related. So it's all protected. So after a certain point, the user space starts, and then the memory is mapped to the user space, which is different memory that's mapped to the kernel space. And voila, there you have Linux or Unix, or it's separation. And the Unix kernel always has better memory, always has more memory allocated to it, even if it's not even using it. It always has faster access time to it because it's always in the lower level of the memory bank. So it's easier to find, and there's less swapping. So the user mode is not going to swap out a kernel level anything at all. It's going to be protected. So here's some more examples of an IBM 370 that has 6 pages to handle an SS move instruction. The instruction is 6 bytes, so it might span 2 pages. So 2 pages to handle the from, 2 pages to handle the to, and then we have 2 major allocation schemes that might be associated with that, and this is what I was kind of alluding to, the fixed allocation versus the priority allocation. So if we have a priority allocation system, that's what I just talked about. If we said the kernel is a higher level priority, and we're not going to allocate, we're not going to swap out any of those frames. Then we're making some frames more important than other frames, which if they're more important, they're not going to be victims, perhaps, so they're not going to be part of the page replacement algorithm. We can also take and separate out and apply different page replacement algorithms to different memory segments and separate the memory per purpose. Or we could take another approach to it in combination. And the interesting thing is these approaches are kind of separate concepts, but a lot of them are done together, is to do a fixed allocation scheme. And fixed allocation just treats everybody the same. Every process gets the same amount. All the memory gets used equally throughout the system. So in terms of a fixed process allocation scheme, we have equal allocation. For example, there are 100 different frames and 5 processes. Each one is going to get 20 frames. So we're going to allocate it all out. No one's going to do that because you're going to give out more frames to different processes that don't necessarily need it. So, I mean, you're going to waste. You're going to have internal memory, leftover frames, perhaps, maybe not. It depends on how much memory you're actually allocating out. Or you could do proportional allocation, allocate according to the size of the process, which is a little bit more efficient. So don't give the process more than the process actually needs. In that case, the size is going to be fixed at a certain length, and then the number, we can actually calculate it out, and I'm not going to go through the calculation, I'll save you that, but we can kind of see, the differences between what efficiency we're going to achieve using one or the other. In terms of the priority allocation, we use and I'm not going to ask you on a final to perform any calculation on estimated access time or number of frames needed or average. You could probably do an average page fault rate if you wanted to. But I'm not going to ask you those questions. Priority allocation. So it basically described it a few minutes ago, but you use a proportional allocation scheme using priorities rather than size. And so we say kernel's got better priority, for example. So if process P1 generates a page fault, select a replacement one of its frames, and select replacement a frame from a process with a lower priority number. So lower priority numbers are freeing up their frames for higher priority processes that are running. So that's usually how it actually kind of works in the true operating system environment, because some things you have to have loaded. So you have to put a priority at one point. So to kind of wrap up the allocation concepts, we have local versus global allocation. In a global replacement, processes are, you select a process for replacement from a set of all frames. One process can take another frame from another, can take a frame from another, meaning it's not set by user. And one of the examples we saw, I had a page replacement algorithm, page table set for one user, and the other user had its own page table. If you're using a global replacement scheme, you could merge everything together and have all processes share all frames. In terms of local, each process selects from its own set of allocated frames. Because the process itself has memory, the process is doing a lot of number crunching, doing a lot of manipulation, and it needs space. It's probably not going to use something else while it's running another piece of memory. So in that particular case, it makes a lot of sense to just have the process manage its own memory space and not go outside in a global. So I've actually already covered thrashing, so I'm going to hit it sort of just kind of quickly to just review it in terms of the definition. If a process does not have enough pages, the page fault rate is very high. It leads to thrashing and leads to low CPU utilization, because the CPU is busy swapping in and swapping out. So that it's busy, but it's not doing anything. So that's why they call it a low CPU utilization. It's not being utilized correctly. It's not efficient. So operating system thinks that it needs to increase the degree of multi-programming. So another process is added to the system perhaps, and that just causes even more problems. So thrashing is a process is busy swapping pages in and out. So here's your definition of thrashing. As the degree of multi-programming increases, it will reduce the amount of thrashing, essentially. So the CPU utilization will come up to a thrashing point, and then increase the degree of multi-programming, which means go switch to another program, create a new process, switch to another process. That helps reduce the thrashing. So demand paging and thrashing. Why does demand paging work? Well, it's locality model. In terms of the locality model, a process migrates from one locality to another. So localities may overlap as well. Why does thrashing occur? Well, because the size of the locality is larger than the total memory size. And we don't have enough memory. So thrashing is a no-brainer. We're going to thrash when we don't have enough memory. And if we have very low level of multiprocessing, it's going to continue to thrash, and it's going to end up with a situation where the computer is just going to turn off. This graph is kind of hard to see, but it says execution time on the bottom. It says page numbers and memory addresses, and it's kind of showing you a thrashing situation where it has to move from one process to another in order to actually remove. And that's why multiprocessing, the degree of multiprogramming, when you increase it, it reduces the thrashing, because you have other things to work with. You're not stuck on that one process. You can just create another process and have that other process do work, which is essentially getting work done, versus the CPU just sitting thrashing on one particular process. We have this thing called the working set model. It's another kind of subtopic that is associated with this. We have a working set window is equal to a fixed number of page references, and so we have, let's say, as an average of 10,000 instructions. The working set model of the process could be equal to the total number of pages referenced in the most recent time of execution, which might also vary. I never actually cover the working set model because it's kind of an old theory in terms of estimating basically level of multiprogramming versus thrashing. So I'm going to kind of skip the working set model because we don't need it for the purposes of this class. But the page fault frequency schemes establish an acceptable page fault rate as a goal of all of these page replacement algorithms. The idea is not to have any page faults, but we're going to have it. And we can calculate the efficiency by the number or by the rate. So if actual rate is too low, process loses frames. If actual rate is too high, process gains frames. And then we can kind of adjust in sort of a real-time fashion. Given the number of page faults, we can apply a different algorithm, or we could possibly tweak the algorithm in terms of its efficiency. So, another related concept is the memory mapped files that we looked at, and that was actually in one of the slides earlier. So the memory mapped files for I/O allows files to be treated as routine access, memory access, by mapping a disk block to the page in memory. So we take something from the secondary storage from the hard drive, we put it up into memory, and that's another way of using memory, and we can map them per process. We can map them in between processes. So we can have multiple processes share the same file in a memory mapped kind of mode. So the file is initially read using a demand paging. Demand pages memory mapped files are not normally written out or swapped. They're sort of a special case in which we're going to load something up in, we have a pointer to it in memory, and we're going to use it. And we're going to use it, and then we're going to close it, hopefully, and take it out. So memory mapped files are generally controlled by the application level, or by the user, or by the kernel who's going to map the file. So the page size is usually proportionate to the file that is read in from the system, from the physical page itself, and so subsequent reads and writes from the file are treated as ordinary memory accesses. So going back to what hopefully I told you at the last lecture, and when we went over main memory in lecture 8, I said that memory that's farthest away from the CPU is the slowest. It's also the cheapest, but it's the slowest access time. So the farthest piece of memory away from the CPU is the hard drive, and those files out there take a long time to read in. So if you want to increase the amount of decrease the amount of time, increase the efficiency of your slower memory, you bring it closer. The only way to bring it closer is to map it. So if you memory map the secondary storage from an operating system's perspective, you've increased the access time. You've decreased the access time. You've made it more efficient. You've increased the efficiency. So you write low-level system call interfaces to read and write, and that's where we get the simplified file access by treating the I/O from memory rather than using a read and a write as a system call. We access it from memory, and we end up with essentially a faster access. So it allows several different processes to map to the same file as well, allowing the page to be shared. So memory mapped files are done for sharing, they're done for efficiency, and they basically are a good concept if you have the memory available. So here we have process A that's in virtual memory, and we have process B that's in virtual memory. And if we load the files in another location, here's our physical memory out here, and we have a disk file that's being loaded. Both processes can access the same file, the same shared memory. And it makes for a lot of file sharing and inter-process communication. If you have multiple processes doing that, you can have multiple processes working on the same job, as I mentioned before. Here's process number 1, process number 2, and here's our shared memory in Windows, where we have a memory mapped file out here. If you haven't noticed, it's kind of it is sort of the same abstraction as you get in most operating systems, but this is basically representing how it's performed in Windows. So we have allocated kernel memory, as I mentioned before. It's treated differently from user memory. It has a higher priority. It's loaded lower in memory. It's often allocated from free memory pool. Kernel requests memory for structures for various different sizes. Some kernel memory needs to be contiguous, just in the nature of how it was designed. And it's usually loaded in the lower box. Another related concept, and what I'm doing now is just kind of going through some miscellaneous related concepts that are associated. No more paging stuff left. The buddy system allocates memory from a fixed size segment consisting of physical contiguous pages, and so we have a memory allocation using a power of 2 allocator. So it satisfies requests in units size of a power of 2. So when the small allocation is needed, when it's available, current chunk is split into 2 buddies to the lower power of 2. So it continues until the approximate size chunks are available. So we keep splitting. We allocate it in power 2 and we split it out to deallocate it, to assign it. Here's our buddy system allocator, our physical contiguous pages. We break it out, we break it out, we break it out again until we end up with a size that's needed for our particular task. for allocation. Another variation on that would be the slab allocator, and these are just different ways of allocating the memory, allocating the frame. So it's an alternative strategy. The slab is one or more physically contiguous pages. So we cache is consistent of one or more slabs. So we use a slab abstraction. So instead of a buddy, instead of splitting it out, we have a single cache for each one of the unique kernel data structures. Each cache is filled with objects, instantiations of the data structure itself. When the cache is created, we fill the objects marked as free. So basically, same concept as before. Call it a free frame, call it a free slab, call it a buddy. They all contain empty frames that we want to fill with information. So here's our slab. So we have 3 kilobit object here, a 7 kilobit object, and we've got slabs here that are allocated. It's just instead of calling it a page, calling it a slab, we're allocating it with a pre-configured scheme. And you might get the impression, hopefully at this point, that every person who creates an operating system has their choice. There's no one way of doing this. And so operating systems vary with their memory management, and which is one of the most significant differences between different operating systems. Especially, given the example I gave you earlier in the lecture, comparing Windows with Java, totally different kind of memory management configuration. And they're specifically designed for the purposes. I mean, Windows is multi-programming. Windows is multitasking, loading up a lot of windows. Java is communication between objects. So everything is a shared memory. In fact, this is a shared memory configuration of Java. Everything is loaded this way. So it's also a Windows kind of scheme as well. So. Other issues perhaps with pre-paging. Paging to reduce the large number of frame faults that occur at process startup. So prepare all of the same, or all or some of the pages a process is going to need before they are referenced. Which means you're going to kind of predict, instead of using a just-in-time, kind of if the memory is available, load it. Thinking it's probably going to use it anyway, hopefully. So maybe other issues may also be associated with the page size, so page size selection. Taking into consideration fragmentation, table size, I/O overhead, or locality. So yeah, the page size is definitely a consideration as well. Maybe looking at a look-aside buffer, transaction look-aside buffer, or some sort of a memory access. So taking a look at the amount of accessible memory from the look-aside buffer, going back to the main memory lecture we had. In terms of the definition of that, can be implemented from a hardware or from a software perspective. We are almost done, so don't worry. I see people looking at their watches already. I normally skip through this stuff pretty quickly because I'm not going to hold you accountable for it. In terms of what you need to get out of this lecture is the main concept of virtual memory and paging. Page replacement as a concept and swapping. These other issues, and I call them other issues, is because it's side considerations, things that go along with the topic that you can implement, in terms of looking at the hardware support, looking at, here's another issue, I/O interlock, pages that must sometimes be locked into memory, not allowing them to be accessed, so considering the I/O itself. Reasons why frames are used for I/O must be in memory in terms of a buffer. We see this in terms of buffered I/O. With not only the disk drive, but with CD-ROM drives and other things. Buffered I/O actually takes memory as well. Is another concept to consider. So, I'm not going to cover the operating system examples because I've given them to you already. We've already talked about Windows and we've already talked about the Unix, but just to kind of put it into a summary for you, Windows does use demand paging. It does it with clustering. And clustering brings a page in surrounding the page fault itself. So processes are designed with a working set minimum and a working set maximum. We have automatic working set trimming that works. So it automatically adjusts, actually. They're supposed to automatically adjust. So, in terms of Solaris, it maintains a list of free pages. It works from a free pages list to assign faults to each one of the process. So, in fact, this is kind of outdated. This is like maybe about 8 years old. So I'm not going to cover the particulars because in each breed of, and this is just Solaris Sun Systems, HPUX, modern day Linux, Unix systems are all going to have a sort of a different configuration. They're all going to use paging, but they're all going to use a separate priority or a separate allocation type scheme. So that is everything you ever wanted to know about virtual memory in Chapter 9. And kind of a long lecture, but it did cover a lot of summary information that hopefully you found helpful. So next week we will move on to a bigger and better topic. I have no idea what it is yet. So questions, comments, concerns? Then we're done. We are done for today. Thank you for staying.